Hello and welcome to this video where we show you the GERSTEL ChomIdent PYRO Edition software. This software enables you the determination of even minor amounts of polymer material and other compounds in complex samples through intelligent matching with library or database data on Pyrolysis breakdown products. This is a recording of a webinar from May 2020 and will give you a very deep insight into the software. Many thanks to our speaker, Dr. Eike from the GERSTEL R&D department in Mülheim an der Ruhr, Germany.
My colleague, Mrs. Wan Shaozu, has contributed a lot to this. I want to thank her at this point for this. Perhaps as an introduction, I think you agree that the pyrolysis of polymeric materials result in complex chromatograms. We have seen this already. And this is true for one polymer, but if we have a mixture of materials and components, the resulting chromatographic situation is getting even more complex. We want to introduce here a new peak-based database approach that helps us to get meaningful data out of this complex situation to help us to identify complex materials. So the starting point could be this one here. This is a chromatogram or pyrogram of an unknown sample. Doesn't look too complex. What would we do? We would use normally we would use the NIST library and to get an idea about the chemical nature behind these peaks, or what are the molecules behind these peaks, and what can we? So that's the first thing we do. If perhaps you can also use literature comparisons for digging deeper in, but first we would do the NIST approach, and this is what we can see from the NIST library. So identification of peaks. From left to right, we see some acrylonitril. Here the identification is not very accurate, but it looks like it is acrylonitril. Then we see butyl methacrylate. We see toluene. This is non-specific. We see styrene. So butadiene, a butadiene dimer, I have to say. So this is a dimer of polybutadiene. And then we see here styrene and higher oligomers of polystyrene. This can immediately be seen with the NIST library. So all these peaks might be markers for polymers. So it might be that polybutadiene was present. It might be that polystyrene was present here. But there are some remaining questions. First question would be, what is with all the other peaks? Are these new components or components, or do they belong already to the already defined or identified components? You remember every polymer decomposes in several, or the decomposition pattern always shows more than one peak. So all these peaks can belong to the already identified peaks, or they can represent new materials. That's the question here. So it doesn't help us. We have to identify these peaks if we want to go ahead manually. And then there's another question. Are all these already identified molecules? Are these really markers for polymers? Or are these also decomposition products from other components or from other polymers? So looks like on the first glance that the information is quite okay, but when we think about it, nothing is clear here. And especially the last point, are these really markers? What we have already identified, I want to dig a little bit deeper into this on the next slides. Especially polystyrene and its oligomers might have different origins, and I want to show you with this picture here. Here you see an overlay of several chromatograms from different kind of polymers and also polystyrene. And you see here the monomer, the dimer, and the trimer from polystyrene. And you see these are also present in the other samples, especially the polystyrene is present, the styrene monomer is present in all other chromatograms, with the exception of for polyvinyl chloride. also the dimer and trimer is present. This is due to the fact that styrene is a simple aromatic compound, and aromatic compounds are formed during degradation of a lot of organic matter. This is here a comparison of the smart ramp pyrolysis chromatograms, but you see the same picture also for this 600 degrees Celsius pulse pyrolysis chromatograms. There, the trimer is heated away, to be honest, but the monomer styrene is present in all chromatograms. So the conclusion is, especially for styrene, the presence of styrene is not a good hint that it was really polystyrene in the sample. We do need to consider all other peaks from polystyrene to be sure about the identification. So these are then the challenges that we have to face when when we have to deal with pyrograms. First, the manual interpretation is very time-consuming, step by step, going through the peaks. Then peaks with low intensity might be missed in this process. Here's an example for this. The upper chromatogram is polystyrene, polyethylene, and a 1-to-1 mixture, and you see the 3 dominant peaks from polystyrene and the regular pattern from polyethylene. And although the mass for both polymers were the same, polyethylene is represented only with little peaks. And if you can imagine if it would be less polyethylene in the sample, we might not see it. The same is true for the lower chromatogram styrene butadiene copolymer. The only thing we immediately recognize is the styrene components, monomer, dimer, trimer, and the or the butadiene components are these tiny peaks here in the early eluting tiny peaks here in front of the styrene peak. So this could be missed when only looking on this chromatogram ourselves. And then last point, we can misinterpret some of these peaks, especially the styrene is a pyrolysate of several polymers. So that's already pointed out here. So this all shouts for library approaches or software approaches for chromatogram comparison, especially for pyrogram comparisons. And yeah, there are approaches available, of course. I'm aware, I remember 20 years ago, there have been approaches where only the chromatography pattern was taken into account. So they used the chromatogram, but only the XY data of the chromatogram. Of course, this is difficult because it ignores the mass spectra, the information from the mass spectra. And it's difficult because when you go from instrument to instrument, when you then retention time shifts or different column chemistry is difficult to handle with this approach. A second approach, of course, is to use average mass spectra. What we do here is we take the chromatogram, the pyrogram, but then transfer this into one mass spectra. So we do an average over the whole chromatogram, an average mass spectra over the whole full chromatogram, and have one plot of for the mass set values. This is a nice approach because it looks like we can load this in NIST-like databases, and chromatogram comparison is then only like the known mass spectra comparison or mass spectra matching. But we have to say this ignores the chromatographic information, because the chromatographic information is lost during this average, during the step of averaging or summing all the mass traces. How this can work, I want to show with this picture or with this slide. So how is the library query done with this average mass spectra approach? First, this is could be a library, so library entries for polystyrene, polybutadiene rubber, and polymetacrylate. And let's say this is the sample. Sample is unknown, but I know it was MABS, the first example, the first chromatogram I showed you here represented as an average mass spectra. So what would we do during pyrogram comparison? We would ask for similarities. Is the mass spectra from polystyrene similar to the MABS sample? No, it's not, and this is true for all the others also. So the result would be there is no match. And that means we have no hint that polystyrene or polybutadiene or PMA was part of our original sample. And the conclusion is, to use this average mass spectral approach, we need to have MABS also as a library entry. Only if we have it as a library entry, we can have a positive match. Sounds logic, but yeah, it's then we have to have all these available mixtures as library entries, and this can be difficult when you think of all the possible mixtures that can be there, all the co-polymers and mixtures with additives or fillers and dyes that are possible in technical products. So this is this approach comes to a limit. And then, yeah, I want to show you the peak-based approach. This is what we want to introduce here. This wants to overcome these problems. We also start again here with a chromatogram, but we transfer this chromatogram in a peak list, and the peak list is have several descriptors: minimum, the retention time, the area, and the mass over set values. And yeah, what's the point here? We compare then for matching these peak lists, and we maintain and use the chromatographic information because we maintain the peaks. And also we use mass spectra because we use them for the peak matching. So with this approach, we maintain the structure of the chromatogram and have the mass spectra information. And we hope this helps to get better information about such technical mixtures like this MABS. How this works, I want to show you with this slide. Let's start how the peak list library looks like. Let's consider this would be the peak list library. It's a list of peaks, the decomposition peaks from the different polymers, and to all peaks, the origin or the source is documented. So we know exactly that this red peak originates from polymer number 1, and that this blue peak originates from polymer 1 or another polymer, or is also present in decomposition chromatograms from other polymers. The peaks are listed in the order of the retention time or the retention index, and the color here should mean it's always the same mass spectra. So also the mass spectra is part of the peak list, or as a descriptor of a peak. So our sample, so first what the software is doing, she's looking for markers. So if we have our library, if we have the list of possible polymers, and then the software searches for markers, for peaks that are unique for one polymer, a peak that only occurs in decomposition chromatograms or pyrograms from one polymer. So the red one here is one marker for the polymer number 1, and the black peak is a marker for polymer number 2. Our sample, of course, is also a row of peaks. The unknown sample, I've listed here a few as an example. And the first step for matching would now be, we would search for the markers. So we search here if we have peaks in the sample that are considered to be markers in our library. So these are the red and the black peaks. So the first hint is with the markers that our unknown sample might contain polymer number 1 and polymer number 2. But as we learned, one marker doesn't mean that it's really the polymer present here. We also have to search for all the other peaks from this polymer, or if also these peaks are seen in the unknown sample. So this is a reverse match. We look if all the other peaks are present in the sample. For polymer number 1, we need to search for the blue peak and the green peak. And also the green peak is can be seen in polymer number 2. So this is the reverse match. And the result now would be, yes, our sample is a mixture. It contains polymer number 1 because it has all the peaks in. It contains polymer number 2. It has all the peaks in. But there's something extra. We see extra peaks which have so far not been assigned to one of our polymers in the library. This is the yellow and the pink peak. So this might be extra components, extra polymers, or additives, or impurities. And this is a complex result, I hope, and which gives us a lot of information about our unknown sample. And so this picture describes basically what, or the basic description what the software is doing. The software itself, we call it Chromldent PYRO bundle. It is a database tool for chromatography data analysis software, which is called OpenChrom GERSTEL Enterprise Edition. The ChomIdent, which is this database tool, is used for processing and comparing these complex GCMS data. With the software, we have a data collection of 100 polymers that is delivered with the software. And all these data are recorded at with two different approaches, one pulse approach and the smart ramp approach. I want to refer here to the lecture on method optimization, for explanation what is the difference between those two approaches. But all the pyrograms are collected here for both approaches. This is a screenshot of a match result which we would get with this software. I want to show you, or I want to give you a brief introduction what we see here basically. So first we see here the library or the reference list. Here it's only a short library with 10 entries, I would guess. Then we see a chromatogram region where sample and references are compared. We see a region or window for the results with similarity index, but most important, a list of the markers I've explained before. We have here a comparison for the mass spectra, a marker peak against a sample peak, which might consider being the same. And we have here the peak list or the sample peak list. And at the end, everything can be summarized in a report. So this is a screenshot, and I want to show you now the same steps I've showed you with the schematic drawing before, what the software is, how the software is deconvolution, or how the software can be used for deconvoluting a complex sample. So the example would again be this MABS co-polymer. So methyl methacrylate, acrylonitril, butadiene, styrene. In our example, MABS as a material was not included in the polymer. Only the pure ingredients have been put into the library. So this is a screenshot. Matching a sample is done with a reduced database of 10 homopolymers, only the pure ingredients. We have reduced here the database to be quick and to show you some how to rule out components and so on. Come to this later. So here the blue circles show the library, and then in the result window, we can look through the marker list, which of these entries have a lot of markers which point to our sample. For example, here PMA, it's highlighted in the blue bar, has shown here 5 markers. And then one of these markers is indeed the monomer. That's fine. So this is a good hint that PMA is really in our sample. And the second hint is that the reverse match factor is very high. So all the peaks that should be present from a polymethyl methacrylate pyrogram are really present in the sample. So these both matches, marker plus reverse match, show us that really PMA is in our sample. And that's the way how we can go through the other lists or through the complete list of markers. For example, the next marker or the next entry with a high marker number is here polystyrene. It has 55 markers here. This is a strong hint that polystyrene is really present in our sample. This is here the monomer, and then the reverse match is also high enough, 63%, and together with the markers, I can say polystyrene is in. Then the next in the list would be here the polybutadiene rubber, present with 14. So polybutadiene would give us 14 markers to our sample. and we really see the dimer, which is a strong hint that polybutadiene is in the sample. And also the reverse match is strong enough. So in total, we can say it's present. So now we found methyl methacrylate and butadiene and styrene in our sample, but there are other entries that also have some markers. Have a look what's here. So for example, polycarbonate. Polycarbonate has 4 markers, but it only has, it has nearly 0 reverse match, or 0% reverse match. So if polycarbonate would be in the sample, we would expect much more peaks originating from the decomposition of polycarbonate that should be present in our sample, which are not. So this is a strong indicator that we don't have polycarbonate in our sample. And the same is true for other indicators, for other entries like polyethylene and so on. I have to say we have chosen here only very short list of entries. The longer the list, the lower the marker numbers gets, and the more accurate the matching results would be. So we have shortened here the list of entries just to get false markers not false markers is wrong. Perhaps not that specific markers, just to show how to rule out components. And the last step we have to do is we have to search for unassigned peaks. We can filter the peak list if there are peaks in which has not been addressed with library entries, or which have no equivalents in the library, and we can see what if these peaks would give us some extra information. When we would do this without software tools, we would do an overlay to search for non-found peaks in the chromatograms. And this is here such an overlay. So we have the MABS sample. This is the red chromatogram, and the so far identified polymers. You remember Acrylonitril was in our sample, but we haven't found it so far because it wasn't in the library. But would we able to find it? Yes, you see here the peaks that have not been assigned so far. And but you remember from the first chromatogram, the first circle, this was the monomer. So as a total result, are we able now to deconvolute our unknown sample? I think yes. With our little test library, we already found 3 polymers, and with an extended library, we also would have found acrylonitril. So the conclusion is it is most likely MABS. This was what the picture we already got with the NIST identification of mass spectra. So there are peaks left with the NIST library. But when you would dig deeper into literature a little bit, then you are also able to identify the rest of the remaining peaks. And now with this full picture, you agree that, I hope you can agree that the conclusion, it is MABS, is true. So yeah, there's so much more to say about the software ChomIdent. So far I have introduced you to the basic functionalities. There are a few things I wanted to highlight here. First of all, I haven't mentioned the software is able to handle data formats from different vendors. So the main vendor chromatography data can be processed directly here. We need to manipulate chromatograms, so we need to integrate peaks. We need to do retention calculations and what else, and retention index calculation. And this can be done in methods, and all the steps can be processed in one method and can be done on single chromatograms or in batches. We have in the software, there are routines for database setups and database queries, and we also provide, there's also a routine for this retention index calculation. I want to point out here, we always need mass spectra. So FID data cannot be processed with ChomIdent. the peak lists can be described by more than only retention time and peak errors. We can bring in peak labels or the retention index and also reference names which can be set manually. So peak lists can have tailored descriptors. The software is able to take replicate measurements into account. So also the variance that occurs when doing replicates runs can be taken into account. This is a strong, feature because peaks that show a huge variance in, for example, area or area ratios can be seen or can be don't have such a strong impact. That's what I want to say here. Match results are visualized here. That's nice to have. Identification of markers I have shown, but this can be used also in a different manner. Consider that all the library would be some polymers of the same basic material, let's say polypropylene. So a lot of technical polypropylenes. Then when you then search for markers, you can find the differences or highlight the differences between the different polypropylenes. And then the software also brings with it a simple PCA tool. It's also nice to have. Yeah, as I said, the basis of all is that we handle chromatograms, that we do peak integration, peak recognition, peak deconvolution, and all the things. This is done with the OpenChrom data analysis, and the ChomIdent software is then a plug-in in this OpenChrom data analysis software. And the OpenChrom data analysis software is also available independently. So as a summary for me, or what is important for us, what can be done with this software? Identification of unknown samples. I think we have shown this already. Then I want to say it's also a helpful tool for quality control because it reveals differences with this marker analysis. That's also very nice. And we can use the peak list, if necessary, as input data for other PCA tools or for the PCA tool that comes already with the software itself. And then, yes, you can test it yourself if you want. If you want to work with your own data, the test licenses are available. And also a tutorial is delivered with the software so that you can find your ways yourself through the software, but we are also happy to assist you. That's was my talk. I want to thank you very much for your attention, for your interest in this topic. And I want to thank my colleagues from GERSTEL, especially Mrs. Huan Shaozu, and also Mr. Philip Winnick from the Lablicate GmbH. In fact, he and his colleagues are the programmers behind the software. Okay, thanks again for your attention.